Hello everyone, my name is Guillermo Reyes, and I'm here to talk about multimodal multi-scale attention guidance for cyber-physical environments, or CPEs for short. In these environments, users often need to find specific places and objects that may or may not be in their immediate vicinity. The larger and more complex they are, the more difficult this will be, as users often become distracted by their surroundings. This is why guiding a user's attention is so important. Attention guidance is the deliberate shifting of a user's focus of attention towards an object or away from distracting ones. But how can an environment do this? We could shift the user's focus of attention by making an object in the environment salient. Without dedicated devices, this could be difficult. But what we could do is make use of the visual and auditive devices that are already in these environments. Unfortunately, some of these devices can be effective at a certain distance or location, but not at another. This is where multi-scale attention guidance comes into play. By taking into account different parameters about the user and the target, as well as the different devices' properties, we can make a decision on what device is most suitable to guide the user's attention towards the object. Our work proposes an attention guidance method that ranks the suitability of visual and auditive devices to guide the user's attention towards a specific target. Now, what is a suitable device? We can imagine how suitable a device is as a function of the user, the target, and a set of context parameters. But even if this function existed, we still don't know what it could look like. Whatever it may be, one could argue that such a function would at least consider two things: how salient the device is, and how close it is to the target. Well, closeness asks the question, how easy can we find the target using this cue? Fairness asks the question, does it attract the user's attention in the first place? We call these two primary functions, and in turn, each of them have secondary functions. I'll now talk about what is meant by these two terms, and I'll start with the visual modality. Let's start with closeness. We tend to think about how close two objects are in terms of distance such as meters, centimeters, and so on. But when guiding a user's attention towards a target, it is also important to consider how easy it is to find the target inside the highlighted area. We assume that the more similar the highlighted area and the target are in size, the easier it will be to find the target inside this area. This describes what is meant by both terms. On the top left is what a perfect cue would look like in terms of closeness. To its right is perhaps the next best kind of cue when we are far away. If we're close enough, perhaps the bottom left would still be good if there is no other option, but this depends on how far off it is, and it should be avoided if possible. Bottom right should better be avoided as it tells the user to look for the target where it's not, and this will just make us lose time. The function could look like the one from suitability before, where we can also have a way to tune how important each of these terms are for our concrete scenario. Now, how can we calculate accuracy? If we were to consider accurate in absolute terms of distance, cues that are near the target will always be the most accurate, while those farther away would barely have any accuracy. This could lead to problems if the user does not see the presented cues or if they lead the user farther away from the target. To counter this problem, we dynamically adapt what is understood as accurate by introducing a sigmoid as a function of the distance from the user to the target. That way, when the user is far away, cues that are near the target are still more accurate, but cues that are farther away are still considered relatively accurate. As the user moves closer to the target, what is considered accurate changes, decreasing the accuracy of cues that are farther away. For precision, the story would be similar. When we are far away, we are less concerned about the precise location of the target. A rough area of where it is suffices. But as we get closer to the target, it becomes more and more important that the area where the user has to search in becomes smaller and smaller. Also, just like there are secondary functions for closeness, we also have secondary functions for saliency. Saliency is based on contrast, things that are different from the environment and just pop out. While there are many features like intensity, color, and orientation which can be salient, we only focus on two: brightness and size. Furthermore, we make some assumptions about the environment and what is salient in them. In the case of visual cues, the first assumption is that brighter cues attract more attention. The second one is that cues that are larger attract more attention. We then can just scale brightness and size of the cue to the range of 0 to 1. The auditive modality is very similar to the visual one. Regarding closeness, accuracy could be considered the same, but we could make a difference in precision. Precision refers to the search area where the user looks for the target. For the auditive modality, it could be interpreted as how good does the cue point us in the right direction. We can apply the sigmoid function in the direction from the user to the target within certain bounds. If the cue points the user exactly in the direction of the target, then this would have a precision of 1. Regarding saliency, we could make the assumption that louder devices attract more attention. One could thus determine how salient an auditive device is in a similar way to brightness. By calculating the sound pressure level, we could predefine a certain number of decibels that make the cue 100% salient. All I have talked about so far is how to get the most suitable device among a set of devices for a user and a target. What I have not yet talked about is how this device changes over time. If we always selected the most suitable device, it could be possible that devices just start flickering all over the place, confusing the user. This is because the environment could be split into hard regions where each region is dominated by one device. To avoid overswitching queues, we introduced a margin. That way, we only switch the guiding queue if we find a device that is more suitable than the one that is currently selected by the certain margin. Additionally, since we eventually want to find the most suitable device, we reduce the margin over time. Finally, the current definition implies that devices could be either only close or only salient. Cases where some queue is too salient but not close to the target would guide the user away from the target. Cases where the queue is too close to the target but is not salient will not attract the user's attention. What we want is something that is both. That way, a sequence of suitable devices would eventually lead to the target. By adjusting the interaction weight, we can decide how important this is at any particular CPE. If it's 0, then the definition is the same as before. If it's 1, then only the interaction term matters. If it's in between, then the individual terms can still make a difference. To test our system, we conducted a user study under different conditions. We had the hypothesis that a mixed modality would provide better performance in terms of distance traveled. We also thought that the lack of an interaction term and a lack of margin would both lead to a worse guiding performance, meaning a higher distance traveled. And we also thought that the lack of a margin would make the system more volatile in terms of a larger amount of cues given to the participant. We divided the participants into two groups, for the mixed and visual-only modalities, and they then completed a series of trials searching for objects in their different interaction weights and margins. A margin of 0.2 was selected, meaning that the queue had to be at least 20% more suitable than its predecessor to be selected. We evaluated this in the context of a virtual reality supermarket. The participants had to move around the supermarket looking for target products while they were being guided by different kinds of cues. This would include ceiling lamps, electronic labels, a series of electronic labels, or a speaker placed behind each of the virtual products that would beep to attract attention. What we got were mixed results. When a margin is fixed at 0.2, a better performance is found in mixed modality independently of the interaction weight. But this was not the case when there was no margin. Furthermore, when a margin of 0.2 was selected, performance in the mixed modality was slightly improved, while in the visual-only modality it got worse. We don't yet know why this was the case. Also, there was a significantly higher number of cues in the no margin condition, which confirmed our hypothesis of the no margin condition being more volatile. The interaction weight did not have a significant effect, so either the parameter did not have a strong influence in guiding the participant, or the design of the supermarket did not present enough opportunities where this could be used. But we should remember that this is a virtual reality environment, and most of the participants had never had such an experience before. To conclude, we introduced a novel method to guide attention in cyber-physical environments, which tries to assess the suitability of a device to guide attention. This method consists of primary and secondary functions. The advantage of this is that the secondary functions can be replaced for better ones without changing the overall method. The initial study we conducted showed some very promising results in the effectiveness of this method, but also some artifacts that need further testing. This of course opens up many new research opportunities like testing the system in the real environment, coming up with new functions, or investigating how this method could be applied to a multi-user setting. Thank you very much for your attention.